At this point with our model, we have a surface normal to describe the direction that the surface is pointing. But what we want to start to do is add light to that. So if you think in terms of the sun being an infinitely far away point, you can take your finger and then go blind looking at it and point at it. And you need a way to be able to describe where that is. So if you are standing there and then pointing at the sun from standing on Earth, if you're pointing straight up, you could define that as a vector right here. Light from above would be 0, 1, 0. That's just pointing directly up. So the x would be 0, the y would be the value 1, significantly going up, and then z would be 0. Or you could say a light coming in from the right. So that would be the x value being 1, or light from below being the y value, again being -1. So we can, just like a surface normal is of length 1, we can define a light direction as being a length 1 unit vector. Now we might want to point it into an arbitrary direction. So we have a normalized function, which GLSL has, or your math library should have in JavaScript. And you can normalize a value. So here's the values 1, 1, 0. If we normalize that, it turns into length 1, so 0.707 twice, and then 0. Then light from bottom right we could define similarly and have it go that way. So now we have two vectors, but we want to compare how those vectors are pointing and determine the light based on those two. So we need a function that takes two vectors and returns a single scalar value, just a number. So instead of two three-dimensional vectors, it returns a single value. And luckily there's a great function that does this for us just fine. It's called the dot product, and it is quite fast. And it's defined here below for an actual implementation in JavaScript. And so the dot product of vector A and B is this math right here that combines them together. And while this might seem a little arbitrary, and I'm not going to describe like how all that works, we can observe what happens as we do this project, combine these together. And here's a ground normal, which is I guess the same as the light from above. So let's go ahead and pretend to console log some of this stuff. So let's do, the ground normal is, if you're the ground, that's the normal pointing straight up. So if you're the surface, the normal looks like this, basically. So let's do a dot product between the ground normal and the light from above. So if you notice, both vectors are going to be pointing up. If you do the cross product of that, the value of that is 1. Okay, let's do the second one. Light from top right. So we have the ground normal, and then we have the light from the top right. We notice that they're at an angle, like the light's coming in from an angle now. So we do it here. It's coming in from the top right, and so it's not going to be quite as bright. If you notice, our dot product says 0.7, so that means it'll be slightly darker. And then finally, if we take the ground normal and do light straight from the right, my image is reversed, so I'm having trouble with right and left here. But if we go directly from the right, then what ends up happening is it would basically miss the surface. The surface would go here and it wouldn't light it at all. And so that is 0. Now what gets weird is if we do the dot product when it's below that, because if you notice the values start turning negative, which is not very helpful for simulating how light works. So if it goes below 0, we should probably just ignore that. So these are useful tools that we can use now. Let's look how we can do that in the fragment shader. So here's our bunny demo again, and you can see it running. What we're going to do is create the light dot product. So GLSL has dot already built in, and we're going to normalize our normal, which we've done before because it could be squished. So we want to get to length 1. And then we're going to take the dot product with a light, which we've set up as one of these arbitrary lights that we've done. We've set it up as a uniform. So that will come in and then determine that dot product that we can then use to light the surface. But finally, that's the dot product again. It can go negative, which will give us things that we don't want. So our surface brightness is the maximum value of either 0 or the light dot product. So if it goes below 0, we just get 0. And so if you want to do kind of, this is called the Lambert shading model. And it's the easiest way to quickly light a surface and play around with it and see it. It's a fairly quick operation that you can play around with the values. And then what I do is I can take a base color, which again I've set as a uniform, which is the XYZ or RGB, which is probably easier to understand. So we can take the RGB values and then multiply them by that value. And multiplying them, if it's 100% light, then that's going to be completely blue. If it's, at an angle, it's going to be less and less and less blue. And then finally, the alpha is going to stay as 1. And I've instrumented this with the DAT GUI, so we can play around with the direction of light, and then it normalizes it for us so we have correct values. So now we can actually light our bunny like a creepy one from below and play around with the values and light it. At this point, a fun way to play around would be to add multiple lights. So you'd have to go through each light that you want to define and then add those values together. You can then start mixing light values together and surface values and play around with different things. And it can be kind of interesting on how you can combine those together. But then that requires a little bit more math and setup of looping through each one, adding them correctly, and working with colors mathematically for the first time can be a little bit confusing because when you're multiplying, things get darker. When you're adding, things get lighter. So you can take some care and play around with like how this can work with a simple model like a bunny to be able to see how you can start playing with light through just math and shaders.